In our last class, we studied about electromagnetic induction's basics, that is the Faraday's laws of electromagnetic induction. And in Faraday's laws, what did we do? We studied two basics law. What are those? First one was that induced EMF produced in any coil across which there is a change in flux involved, right? And the second law was, the first law also inculcated the fact that the induced EMF will be lasting till the time the change in flux is continuing across the area loop, right? We also discussed about magnetic flux, which is magnetic field into area of cross section. The third thing was the magnitude of induced EMF. We did an expression for that is the mathematical form of Faraday's law. Induced EMF is directly proportional to rate of change of flux, through which we devised this formula, minus d phi over dt. Now in this formula, this negative sign was given by Lenz law. So we'll start this lecture from Lenz. What is Lenz law? See, note down the statement. Lenz law states that induced EMF always appears in such a direction so as to oppose the cause responsible for its production. Few major points, few important points in this, that induced EMF always appears in such a direction so as to oppose the cause responsible for its production. This is how induced EMF is to be formed. Now, how do we calculate the value of induced EMF if we have a magnetic field and an area? First of all, magnitude was given by Faraday's laws, very well. The direction is defined by Lenz law, right? No, Lenz law gave the statement that induced EMF is always going to be opposite, but the actual magnitude was given by Flemings right-hand rule. And what is Flemings right-hand rule? Though we are going to do it again in detail, but listen to it. What was the Flemings left-hand rule for magnetic field, force and the direction of charge? That was force, field, current. Thumb was representing force, first finger was magnetic field, and middle finger is direction of flow of charge, that is current. Here, only thing changing is, this is motion, field, current. What is this? Motion of that is the way loop is changing in the magnetic field, then magnetic field direction and more current, the action of flow of current. So this will give you the direction of induced EMF or induced current, and this is motion and this is, so only difference is this is force field current and this is motion field current. In camera, like you guys, like this might be looking to you as a left hand, but my right hand. So adjust it. Left hand rule states, now look at this, left hand rule says force field current and right hand rule says motion field current. Okay, we'll go back to it. We'll do some practical live numericals. First, there is a statement and a very important question about Lenz law. This is Z, the Lenz law. First of all, statement is, I'll repeat it for the last time, that Lenz law states that induced EMF always appears in such a direction so as to oppose the cause responsible for its production. The question is, show that Lenz law is in accordance with the law of conservation of energy. Accordance with law of conservation of energy. Now, why this question is even important? Why is this question even existing? What has Lenz law got to do with the law of conservation of energy? See, I'll explain. We have a magnet, which is this, North Pole and South Pole, and we have a loop here, this much far, okay? Let us say right now only two magnetic lines of force are passing through this coil. That means flux is equal to 2. What is flux? The number of lines passing through the surface, right? Now I have brought this magnet closer like this, and now my magnet is this much near, and this time the number of magnetic lines of force which is passing through the loop, let it be 10. Flux is 10, right? What has happened till now? Only the number of lines which is passing through this loop is changing, or has changed, and due to this there is a flow of current, there is a current, existing current in this loop. This current, that means voltage, that means power, that means energy, they are all interlinked, right? So this energy is caused by the movement of this. Initially it was considered that this is a natural occurrence of energy, and we know the law of conservation of energy, that energy can neither be created, it cannot be destroyed, it can only be transferred from one form to another. So if you do not consider the motion of magnet, then you will find an appreciable amount of energy getting produced in the wire without any cause. So that was a clear violation of law of conservation of energy. So that is why this question was clearly stating that what is Lenz law? Show that the Lenz law is in accordance with the law of conservation of energy. The answer would be Lenz law statement, you already know. The question also is asked in this way: does this law violates the law of conservation of energy? That is the more common form of this question. So the answer would be no. Lenz law do not violate the law of conservation of energy. Why? Keep this thing in mind. Actually, no law in this world violates the law of conservation of energy. There are many tricky questions in your competitive exams where they precisely ask this. They'll try to change the values of a equation and they'll ask you, can this law violate the law of conservation of energy? Well, if the equation is dimensionally correct, then there will be no violation, because law of energy is never violated. All right. Coming back to this question, when the magnet is brought closer to the coil, the mechanical work done. What is mechanical work? It is a form of energy, mechanical energy, right? So when the magnet is brought closer to the loop, mechanical energy involved in doing this process gets converted into electrical energy in the loop. I'll repeat. When a magnet is brought near the coil, the amount of work done in bringing the magnet closer to the coil or away from the coil appears in the form of electrical energy in the coil, and hence energy is only getting transferred from one form to another without any appreciable loss. So that means it is not violating the law of conservation of energy. It is not producing energy automatically. It is there because one form of energy is getting converted into another form. All right. This was the explanation of this question. Now coming back to the explanation of motion field current. Okay, let me write it first of all. This is called Flemings right-hand rule. What does this rule states? This states the direction of induced EMF or induced voltage, right? Fleming's right-hand rule. According to this rule, thumb, first finger and middle finger. Thumb corresponds to direction of motion of conductor, because generally what I was doing, what I was bringing the magnet closer to the loop, right? But generally we do not do so. We make magnets are what? Magnets are those devices or those products used in the experiments from which we are getting the magnetic field. We are not going to move the magnetic field or the source. What we can do, we can rotate the coil itself, and accordingly that, because that is more convenient, we can change the number of loops, we can increase the area of the loop, we can do anything with that. That is why we do not move the magnet. So when I was doing this, I was explaining you this thing, that direction of motion